Partial differential equations. Partial differential equations are used to solve physical and other problems involving functions of several variables. Partial differential equations can be used to describe a wide variety of phenomena such as sound, heat, diffusion, electrostatics, electrodynamics, fluid dynamics, plasticity, levitation, and quantum mechanics. Ordinary differential equations often use model as one-dimensional dynamical systems, and partial differential equations often use model as multi-dimensional systems. Now, let's discuss about partial differential equations. First, we define what is partial differential equation. A differential equation which involves partial derivatives is called partial differential equation. For example, x del z by del x plus y del z by del y equal to z. Del 2z by del x2 plus del 2z by del y2 equal to 0. For example, del 2u del x del y equal to del u by del z equal to. In all these examples, equations involving partial derivatives of z with respect to x and y respectively. So these examples represent partial differential equations. If z is a function of two independent variables x and y, then we should use the following notation: the partial derivatives of z. Partial derivative of z with respect to x is equal to p. Partial derivative of z with respect to y is q. Partial derivative of z with respect to x, the second order represented as r. Partial derivative of z with respect to both variables x and y represented as s. Partial derivative of z with respect to y, the second order represented as t. Now, we shall discuss about order and degree of partial differential equations. First, order of a partial differential equation. The order of a partial differential equation is the order of the highest order partial derivative occurring in the partial differential equation. As degree of a partial differential equation. The degree of a partial differential equation is the degree of the highest order partial derivative occurring in the partial differential equation. First example, del z by del x plus del z by del y equal to 1. In other form, we can write this partial differential equation as t plus 2 equal to 1. In this example, highest order partial derivative is 1 and its degree is 1. This is partial differential equation of first order first degree. Second example, del 2z by del x plus del 2z by del y2 equal to 0. In other format, we can write r plus t equal to 0. In this example, the equation contains highest order partial derivative is second order and its degree is 1. This partial differential equation is of second order and first degree partial differential equation. Third example, del 2z by del x2 plus 6 del 2z by del x del y plus 5 del 2z by del y2 equal to 2x plus 3y. Differential equation can be written as in other format as r plus 6s plus 5 equal to 2x plus 3y. The highest order of partial derivative is 2 and its degree is 1. This is partial differential equation of second order first degree. Fourth example, 3 into del 2z by del x whole square plus 4 del z by del x equal to 0. In other format, we can write as 3p square plus 4q equal to 0. And this partial differential equation, highest order partial derivative is first order and its degree is 2. So this is partial differential equation of first order and second degree. Now we shall discuss about formation of a partial differential equation. A partial differential equation is formed by elimination of arbitrary constants or the elimination of arbitrary functions from a relation involving 3 or more variables, say x, y, z, etc. If a relation of variables is given, we can constitute a partial differential equation by methods elimination of arbitrary constants or the elimination of arbitrary functions. Now we shall use first method. The type first is formation of the partial differential equation by the elimination of arbitrary constants. The first problem is find the partial differential equation by the elimination of a and b from the relation z equal to ax plus by plus ab. Its solution means we have to form a partial differential equation by elimination of arbitrary constants. So first we write relation z equal to ax plus by plus ab represent as first equation. Differentiating this relation 1 partially with respect to x and y, we get del z by del x equal to a and other variables kept as constant, so result is 0. We represent this result as p. Similarly, differentiating partially with respect to y, we will get del z by del y equal to b represent as p. Both results represent by equation number 2. Now we can eliminate the constants a and b easily by p and q with the help of equation number 2. So from 1 and 2, the required partial differential equation is z equal to px plus qy plus pt. This is our required partial differential equation. The second problem is Az plus b equal to a square x plus y. We have to form partial differential by elimination of arbitrary constants. First, we write given relation Az plus b equal to a square x plus y, represent as equation number 1. Now partially differentiate 1 with respect to x and y. We get result as equation number 2, p equal to a. Result equation number 3 is q equal to 1 upon a. From 2 and 3, we will obtain the relation p2 equal to 1. Yet b cannot be eliminated with the help of p and q. So we shall not use relation 1. We shall use results 2 and 3 to constitute required partial differential equation. As 3 problems for practice purpose. Z equal to ax plus a square y plus b. Second problem, z equal to ax plus 1 minus a y plus b. Third example, x minus h whole square plus y minus a whole square plus z square equal to h. And this problem differentiate partially with respect to x and y and eliminate the constants h and k only to get new partial differential equation. In first method, a relation involving arbitrary constants, we can constitute partial differential equation with the help of elimination of arbitrary constants. Now we shall use second method, that is type second, formation of a partial differential equation by the elimination of arbitrary functions. The relation involving is arbitrary function. First problem, find the partial differential equation by the elimination of arbitrary functions from relation z equal to f of x squared plus y squared. The right hand side, f of x squared plus y squared is the arbitrary function. You can replace a by any one of the function, trigonometric, exponential, and other type of algebraic functions. To constitute partial differential equation, you will eliminate arbitrary function. So we first write given relation as z equal to f of x squared plus y squared, represent as equation number 1. Differentiating 1 partially with respect to x and y, we get del z by del x equal to, we first partially differentiate f dash x squared plus y squared, then x squared plus y squared partially differentiate with respect to x. To get the result is e equal to 2x f dash x squared plus y squared, represent as equation number 2. Partially differentiate with respect to y, we get del z by del y equal to, first partially differentiate with respect to y, we get f dash x squared plus y squared, and x squared plus y squared partially differentiate with respect to y. Then result is 2 equal to 2y f dash x squared plus y squared. This equation represents as equation number 3. Now equation number 2 and 3 represent first derivative of arbitrary function. With the help of these two equations, we can eliminate arbitrary function and we shall get the relation is p by simplify to get py minus 2x equal to 0 or py equal to 2x. This is the required partial differential equation. The next question. Z equal to y square plus 2 into f of 1 upon x plus log of. In this problem, arbitrary function is also involved. So to constitute partial differential equation, we say eliminate arbitrary function. So we first differentiate partially with respect to x and y and eliminate arbitrary function. The first write given relation z equal to y square plus f of 1 upon x plus log of y. Represent as equation number 1. Differentiating 1 partially with respect to x and y, we get del z by del x equal to, first term is 0 because it is constant, plus 2 into partially differentiate with respect to x. So result is f dash 1 upon x plus log of y, and 1 upon x plus log of y partially differentiate with respect to x. The result is minus 1 upon x square plus 0. The result is p equal to minus 1 upon x square 2 into f dash of 1 upon x plus log of y, represent as equation number 2. The result is minus px square equal to 2 into f dash of 1 upon x plus log of y. Similarly, del z by del y, the result is 2 equal to 2y plus 2 upon y f dash 1 upon x plus log of y. This result represent as equation number 3. In both results 2 and 3, arbitrary functions are involved and this can be eliminated. So eliminate arbitrary function, and the result is, final result is 2y equal to 2y square minus x square. This is the another problem of formation of partial differential equation. Form a relation with the help of elimination of arbitrary functions. Another problem. Z equal f of x plus ay plus phi of x minus ay. This relation involving two arbitrary functions. So we need to eliminate two arbitrary functions. So we differentiate partially 2 times with respect to x and y, then eliminate these two arbitrary functions from the relation and to get partial differential equation. We first write given relation z equal to f of x plus ay plus phi of x minus ay. This is represented as one equation number 1. Differentiating 1 partially with respect to x, we get del z by del x equal to f dash x plus ay plus phi dash x minus ay. Again differentiating, the result is del 2z by del x equal to f double dash of x plus ay plus f double dash x minus ay. Differentiating 1 partially with respect to y, the result is a into f dash x plus ay minus a phi dash x minus ay, because this is the partial derivative of z with respect to y. So x kept as constant and ordinary differentiation with respect to y. Similarly, second order partial derivative del 2z by del y2, the result is a square f dash x plus ay plus a square phi double dash x minus ay. The result is a square common out, and the result in bracket f double dash x plus ay plus phi double dash x minus ay represent as equation number 3. From 2 and 3, we can eliminate arbitrary function. The result is del 2j by del y2 equal to a square del 2j by del x2. In other format, t equal to a square into r. The other problem, z equal to f of x plus iy plus capital F of x minus iy. This can be solved as previous question, because this problem is also involving two arbitrary functions. Next, we shall represent parametric equations of a function. Sometimes problem involving the use of parametric equations. If u is a function of two variables x and y and written as u equal to f of xy, where x is function of t, phi 1 t, y is also function of t, phi 2 of t. X and y is other function of other variable t. So these two equations are called parametric equations, and the new variable t is called parameter. Then we can find total differential coefficient du by dt. Du by dt is the total differential coefficient. This can be written as del u by del x dx by dt, because x is function of single variable, so ordinary derivative, plus del u by del y dy by dt, because y is the function of single variable t. If the independent variables are functions of more than one variable, then we can adopt same rule. U is function of x and y, and x is function of t1, t2, that is phi 1, t1, t2. Y is function of two variables t1, t2, and y is phi y equal to phi 2, t1, t2. T1 and T2 are two independent variables, and x and y are functions of T1 and T2. So these two relations are called parametric equations, and new variables T1 and T2 are called parameters. So we can find total differential coefficients of u with respect to T1 and T2 respectively. But notation is represented as partial derivatives, because x and y are functions of more than one variable. So del u by del t1, this is the total differential coefficient of u with respect to t1. T1 is the parameter. The result is del u by del x by del t1 plus del u by del y by del t1, and both terms we have written partial derivatives of x and y with respect to t1, because x and y are functions of more than one variable, so we should write partial derivatives. Similarly, del u by del t2, this is the partial differential, total differential coefficient of u with respect to t. So del u by del t2 equal to del u by del x by del t2 plus del u by del y into del y by del t2. Here x and y are functions of more than one variable. So in the result, we shall write partial derivatives of x and y with respect to t2. Similarly, this can be adapted for other functions in the same manner. The first problem is find partial differential equation of a for x square plus y square z minus xy equal to 0. This relation involving arbitrary function, but this arbitrary function also involving some complicated variables. So we shall replace the relations by new variables. Suppose u equal to x square plus y square and v equal to z minus xy. Then the result is f of uv equal to g. This is the first relation. So f is a function of u and v, and u and v functions of three variables x, y, z. So these are parametric equations. We first differentiate one partially with respect to x. We get del f by del x equal to 0. Here del f by del x is the total differential coefficient and x is parameter. We shall use concept of total differential coefficient. The result is del f by del u, del u by del x, del f by del v, del u by del x equal to 0. Here x is parameter and f is function of u and v. Substitute the results to get equation number 2 as del f by del u into 2x, del f by del y, del f by del v into e minus y equal to 0. Now differentiating one partially with respect to y, we get del f by del y equal to 0. Here y is treating as parameter. So this is total differential coefficient. Del f by del y is total differential coefficient. So use concept of total differential coefficient. The result is del f by del u to del u by del y plus del f by del u, del v by del y equal to 0. Use concept of partial derivative. Result is equation number 3. That is del f by del u into y plus del f by del u into 2 minus x coefficient. From equation 2, we can write del f by del v upon del f by del u equal to minus 2x upon minus y. And from equation 3, we can write del f by del v upon del f by del u equal to minus zy upon 2 minus x. Now these two relations substitute partial differential equation with the help of elimination of arbitrary function. To eliminate the arbitrary function f from these two relations, we get minus 2x upon e minus y equal to minus 2y upon e minus x. The final result is 2x minus x equal to 2y e minus y. The other problem is vector f of xy plus z square x plus yz equal to 0. The relation is f of xy plus z square x plus y plus z equal to 0. Here the same problem. We can use concept of total differential coefficient. The variables u and v represent as complicate relations. So u equal to xy plus z square, v equal to x plus y plus z. Then the relation is modified. Uppercase letter f of u equal to 0. This is equation number 1. So use del f by del x. The x is parameter, and del f by del x represents as total differential coefficient. And use concept of total differential coefficient. The result is del f by del u, del by del x, del f by del v, del by del x equal to 0. Partial differentiations of u and v respectively. Substitute the results. We get equation number 2. Del f by del v del f by del u minus y plus 2zv upon 1 plus b is equal to as. Similarly, we shall take del f by del v, del y equal to 0, del y is parameter, and del f by del y is total differential coefficient. So use concept of total differential coefficient. The result is del f by del u by del y plus del f by del v, del u by del y equal to 0. Use partial derivatives of u and v with respect to y and substitute the particular place to get the result is equation number 3. Del f by del v upon del f by del u equal to minus x plus 2z whole upon 1 Now equation number 2 and 3 is partial differential with the elimination of arbitrary function. To use equation number 2 and 3 and eliminate arbitrary function. Result is minus y plus b plus p equal to minus x plus p to the power minus q. Simplify, we get p into x minus pj plus q into pj minus y, so y minus x. Here, partial differential equation can be obtained by two methods. One is elimination of arbitrary function, another is elimination of arbitrary functions. It is depend on the problems. The problem containing arbitrary constants is eliminate arbitrary constants. The problem containing arbitrary